Okay, can you see my screen?
Yeah, perfect. We can hear you and we can see your PPT deck. Yeah.
Okay, perfect.
Mm.
All right, I'll go ahead and start. Hello,
Yeah, Eden,
everyone.
you may use 1 minute to introduce yourself. Then you can go ahead to present this paper. Yeah.
Okay,
Mm,
perfect. I'll do that.
mm.
All right, so hello, everyone. My name is Ethan Floor, and today I'm going to be giving my presentation on the paper about Faasm, um, which is lightweight isolation for efficient stateful serverless computing. And before I start, I'll go ahead and give just a brief introduction of myself. Again, my name is Ethan Floor. I hold two bachelors, one in computer science and one in statistics, both of which are from FIU. Currently, I'm a graduate student also at FIU in cybersecurity, and this is my second semester. In terms of my interest, I essentially love anything that has to deal with data science. So big data, machine learning, AI, and databases. And in the future, a near future, I expect to be a data scientist. Okay, so just as a general outline for today, we'll first start by going over some background information on the topics of serverless computing, cloud infrastructures and their services and specific cloud functions. And we're going to see some of the pros and cons of serverless computing. Next, we'll go into what is Faasm and discuss the previous research attempts, the features and benefits of the Faasm system and its components. Next, we'll transition into how it actually works and how it comes together, and then look at the results of it and some of the experiments that the author did, and finish up with a short summary and have our discussion, questions and answers at the end. Okay, so what is serverless computing? Serverless computing is essentially a type of service that allows users or individuals to deploy their code or applications without really dealing about the physical hardware or computer infrastructure that surrounds the environment. A common use case is to simply take a single server or several servers in the form of virtual machines and spin them up with a given configuration based on the task you're trying to accomplish and use their resources. Likewise, we'll only pay for the resources we use, which is one of the benefits of serverless or cloud computing, and only for the time we use it. Now, to make this possible, we need a serverless provider. So um, there are several organizations and companies that provide these services. Some of the largest in the industry and occupy the largest market shares include Amazon Web Services or AWS, Google Cloud Platform from Google, and Microsoft Azure, of course, from Microsoft. Now, as the popularity of serverless computing grows and data-intensive applications continue to grow in a data-driven environment we live in today, more and more specialized services have come around and emerged as a result. One of the common ones are cloud functions. And essentially, these cloud functions, unlike as we saw previously, spinning up a full virtual machine in the cloud, these are actually single purpose or single use that can just take your user code or applications code basically in any language without the need of a virtual machine, and the containerization will be taken care of by the provider itself without any user intervention. And on the right, we can see three proprietary versions of these. From Amazon, we have AWS Lambda. From Google, we have Google Cloud Functions. And from Microsoft, we have Azure Functions. And these functions are scalable, so we can run as little or as much as we need. And now going into the pros and cons of serverless computing. While serverless computing does provide several benefits and advantages, um, there are some consequences of it. Um, First of all, in terms of advantages, again, we don't have to have any managed infrastructure. It's completely scalable in both directions, so upwards and downwards, and we use as much as we need whenever we need, and likewise, we'll only pay for what we use. Now, in terms of consequences, um, there is a lot of overhead and resources that are used to spin these up in the cloud. So the first factor is computation time. So the amount of time we're spending to process our application and our code. Next is our memory. So our memory can come from a variety of places. The first of which is our code. The next is our data. So the data that we have to make our application run, or the data we're producing if we want to save it onto our system or onto memory. Next, there are external libraries. So any external functions or code that's needed to make our application run, and any shared resources between hosts or machines. So all of this together adds up to extremely high overhead costs and can reduce efficiency when we're actually dealing with processing functions and data intensive applications. So some previous attempts that, or previous research attempts that tried to solve these issues, we'll talk about a few of them. We have Pyren, which essentially decided to reuse containers for functions. They'll reuse the containers, but the con is that there's no shared memory between them. So if we want to have shared memory between hosts, it'll be very redundant, and that'll cost more and be inefficient. Similarly with Crucial, we're essentially sharing VMs between functions, but there is still a problem with shared memory and security of the memory. For Cloudburst, it also decides to share the VM between functions, but it now uses a key value cache to improve efficiency. But we're still left with the issue of sharing memory and having memory security. Next up, we have Crustlet, which essentially replicates containers for as much functions as we need. And it also provides memory safety. But on the downside, we have still a large overhead to deal with. Last up, we have SUSE, which is essentially a single unikernel, a very lightweight kernel, and we can restore and use snapshots of virtual machines, um, and as a result, that'll be very fast to run, but we now don't have any isolation. Okay, this now brings us to Faasm. So Faasm in itself refers to the full system or architecture that allows for the serverless processing of the functions. The author refers to Faasm or Faasms individually or in components by the name of Faaslets. Um, Overall, we have memory isolation that's split either between hosts or functions, and it's dedicated to a specific function, all of which is run within a thread or control group within a Linux environment. And this entire function or entire system, I should say, provides isolation via a host interface. And essentially, this is just an API system which we can make system calls to interact with our memory, our network, and our file systems, which is as seen on the right. And this is all completely isolated from one another. Okay, so what is the benefit of Faasm and this architecture? So Faasm provides essentially four main benefits. The first of which is lightweight isolation. Um, Next is efficient local and global state access, fast initialization times, and a flexible host interface. So now let's take a look at what actually fuels or provides these benefits within the Faasm environment. So in terms of isolation and local global memory access, this is coming from the specific memory structure of Faasm. So if we have a scenario where we have two functions we would like to run, and we want to ensure that each individually has access to its specific data and also has a shared memory component, which focuses on the efficiency of it, we can just have a simple memory vector where we can map the respective components to. So as seen in the top diagram, the blue portion of the memory gets mapped only to function A or Fazlet A, and the orange portion will get mapped to only Fazlet B or function B. And now we have a shared component, which is the green portion, and it will map to both of them. So this is, as an example, in the case if we have shared data for both Fazlets. And now the beauty of this is that we can actually extend this concept to several machines or several hosts. So if we move over to the bottom diagram, we now see that we have two uh, hosts with four functions, F1, F2, F3, and F4. And similarly, we would have the blue memory portion occupied only in host one, and the green occupied only by host 2, with the orange components shared between both host 1 and host 2. And now looking at the host interface of Faasm, there are several calls and states which we can use in order to change the data as our function is updated or as we're progressing through our application. So all of this adds up to its stateful property. So in other cases where we have a VM, we don't have any control. We would simply run a function and there's no way to interact with it. And as an example, to give clarity on the host interface in action, if we have a use case, a code snippet here written in Python for machine learning training, specifically on the stochastic gradient descent algorithm, we want to make sure that after every iteration, we can actually update and keep track of our machine learning weights. And we can see this is achieved in line 13 as we can actually push our local data into our global data. And similarly, if we want to run this, if this is data intensive and we want to run this in parallel, we can actually chain functions and supply the amount of parallel process we want and for a given amount of time. And we see this in the definition created for line 16. Okay, so how does all of this actually come together and how does Faasm actually work? So to start, we would have our source code or our application or function code, either or, and we'd use the author's Fazlet toolchain to compile these our source code or our code into binary instructions via WebAssembly. And now that we have binary instructions from WebAssembly, we can create an object um, from these instructions so that it can be interpretable at the machine level or virtual machine level. And then we can link all of the excess machine level code so that we can produce our executable and actually run it. Okay, so now let's take a look at some experiments and results associated with Faasm. The first experiment, as we see here, is to compare a standardized workload across widely used Docker containers and the author's version of Fazlets and proto-Fazlets. Namely, the workload is a no-op or no operation function, and it's essentially just a command at the assembly level language that just does nothing. It just has a baseline. And for reference, proto-Fazlets is just the name given by the author to refer to Faslets that originate or are initialized from a snapshot or a backup of a pre-existing Faslet. So if we compare the performance of proto-Faslets to Docker, we actually see a significant improvement across the initialization time. So around 5,600 times faster initialization time. In terms of CPU cycles, we see around 385,000 times less cycles, so from 251 million to only 650. For PSS memory, which is just proportional state size, it's just the memory occupied in RAM by the process. We see about a 15-fold decrease in the usage. And for RSS memory, which is just resident state size memory, the portion that's held in RAM by the processor function, we see a 57% decrease in the amount of use. And lastly, for capacity, which is just referring to the amount of containers or faslets we can have on a single host, we see a 12-fold increase. So on Docker, we're limited to about 8,000 containers on a given system. And for proto-faslets, over 100,000. The next experiment is meant to compare the latency, the latency time experienced when creating and deploying several applications or containers within Docker, Faslets, and proto-Faslets. Starting with Docker, we see that about every 1,000 milliseconds of latency will increase beyond for every 2 seconds. So we'll have a container generated about every 2 seconds and have about 1,000 milliseconds of latency associated with that. Moving on to the orange line, which is Faslets, we see that there's a more stable latency. There's not much jumps with it. And we maintain this threshold up about 600 Faslets per second. And we see even better performance and stability with proto-Faslets, and we maintain this latency threshold at about half a millisecond up until about 4 or 5,000 proto-Faslets generated per second. Now, this last experiment is depicting the performance of Faasm across data-intensive machine learning training. Similar to the Python code we saw, it's the same stochastic gradient descent algorithm. Both Faasm and Knative are now compared. Knative is just similar to Docker, except it helps manages several containers, and instead it's run on instead of Docker, it's run on the Kubernetes platform. Starting with A on the left for training time, we see that if we increase the amount of functions we're running in parallel, we don't really see any spike in time. Network the same thing is observed. Faasm is very stable in the amount of data transferred between the network, regardless of the amount of parallel functions we're using. And this actually isn't the case in Knative as we see this increase. And lastly, in terms of memory usage and memory consumption, Faasm maintains very low memory usage with the same trend of stability, regardless of how many parallel functions are run. And this is the opposite case when used in regular containers with Knative. All right, to conclude, so just a brief summary of what we've seen with Faasm. Faasm serves as a high performance environment for data intensive computations. Faasm also provides scalable and efficient parallel processing. And lastly, Faasm can uniquely share memory across hosts and functions while also ensuring memory safety.
Okay, then thanks
So,
for this presentation. Can you
thank
could
you.
you go back to the slide about the memory architecture?
Sure.
That page, yeah.
This one.
The previous one. This one, yes.
Uh, this one?
Uh, this one, yes.
Okay.
So I think this is the core part of the design the system, right?
Yes, this is the essentially the powerhouse of the research of Faasm.
Yeah, I think so. For the top part, it's easier to understand, right? They separate the memory for the private part and the shared part. But for the below figure, so how did they design to like the process can share the memory across different hosts? Did you check that or?
Yeah, so it's
Mm.
essentially extending the same idea. So when they're coding it in WebAssembly, um, because it's still low level, it's just a memory vector or memory array, and they're
Mm-hmm.
now isolating this. So this memory function or memory array that we see in the first or top level
Mm-hmm.
is local. So it's local to A and B. But now we have a separation or isolation, which is on the global tier. And we're essentially mapping this into different hosts. And between hosts, we can also map them to functions. So we have essentially, when we're doing it between hosts, we have another level of isolation if we want between functions.
Okay, so they will always keep this mapping, right, between this local tier and
Yes,
the global tier. Oh, okay,
exactly.
okay, okay. Yeah, it's good to know. So, and then can we go to there is another page is about the code compilation. I think the next
Oh,
following. Yeah.
not this one.
Not,
You mean the diagram?
yeah, this one I think. So in this page they mentioned this untrusted and trusted. So what's the meaning about this information?
I honestly didn't get a chance to look at this, but
Yeah,
from
I
what I'm
think they
assuming,
mentioned should be related to this web assembly, right? And then
yes,
yeah.
I believe there's a difference because you're taking your code initially, and
Mm-hmm.
then we're uploading it or converting it to WebAssembly. So as soon as we have it in WebAssembly, it's now a lower level and it can be trusted or
Yeah,
used
it's turned
by
to the trusted one. Yeah.
it turns into trusted and it can be used by the machine.
Yes. Okay. So next, can we go back to the comparison between this Faasm and the container? Should be a table on the slides. Yeah. I think the following page.
This one.
Yeah, this one. I can from this comparison result, I can understand for this initialization memory and the capacity, but for the second row, you see it's a CPU cycles, right? For Docker is a 200 million something, but for the fastest it's just 1.4 KB. So did you check why the difference is this huge, right? You can see VS to Docker is a five is a three more than about 400K difference. So
Yes,
yeah.
it's a huge difference actually. So
Mm-hmm.
the author essentially the reason behind this is that the type of isolation in terms of memory and Docker is much more heavyweight than it is implemented between the
uh,
Faslets and
mm,
proto-Faslets. So whenever we're spinning up, because we're starting off all of these containers cold, so we're not initializing them from a previous or previous runtime. So it's just from the start as
mm,
is. So that's why it's more heavyweight on Docker than it is
mm,
on these Faslets and proto-Faslets.
yeah, yeah, makes sense. Yeah. Okay, I do not have any other further question. So other students, if you have any question, we can discuss here. Uh,
Um, I noticed there's an actual GitHub for using Faasm. Have you tried looking into how fast it is compared to actual Docker? I'm not sure if you're familiar with working with Docker. Just out of
Yeah,
curiosity.
so I actually did. Yeah, I have used Docker very briefly for a few projects. I actually looked at the GitHub. It's publicly available and open source. There's a lot of steps, honestly. It's a big learning curve to use it.
Yeah.
There's a lot of steps because this is very recently developed a topic. But I would assume, of course, I promised this table, if we were to compare it and use similar functions, we would see a similar